Okay, in this lecture we're going to cover electric fields in 2 dimensions. You can also find the electric field due to 2 or more charges that do not fall on a line. The electric field is represented by vectors at every point in space. It will be calculated at a specific point in space. There doesn't have to be anything there. Once again, we start by establishing perpendicular axes that are symmetric to the problem. So first, let's determine the field at point C due to charges A and B. A, B, and C are on the corners of an equilateral triangle of length r. Note that there is nothing at point C. First, let's overlay an appropriate coordinate system and draw the electric field vectors at point C due to the 2 charges. Okay, so now let's show the vectors of the electric fields due to charges A and B at point C. Here we have the x and y axes located with the origin at point C. So now we have the electric field from A and the electric field from B. To find the vector components of EA and EB along the coordinate axis of vector C, we're going to have to use our trig functions, sine and cosine. Okay, we know from the fact that this is the equilateral triangle that this angle is going to be 60 degrees, this one too, and that means that this angle is going to be 30 degrees. It doesn't matter which angle you use. You can use the 30 degree and then the opposite side is the x component and adjacent side is the y component, or you can use the 60 degree angle where the opposite side is the y component and the adjacent side is the x component. It doesn't matter. So how were the angles assigned to the triangles made by vector components E and EB? Well, the interior angles of the equilateral triangle are all equal to 60 degrees. The base of the triangle is parallel to the coordinate system at point C. By the math theorem that deals with corresponding angles, the angle at point A is equal to the angle made by EA and the x-axis at point C. Again, it's your trigonometry, or maybe you covered that in geometry. Okay, now we can use our trig functions to take the vectors and break them up into components. The next slide shows a vector representation of the solution. Okay, so first thing we're going to do is we're going to find the x components. So you take EAX and EBX. Here it's going to be the cosine of 60 degrees times E. This is going to be negative E times the cosine of 60 degrees because it's pointing west instead of east. That gives us 0. Okay, now if you look at the y direction, which you can see right here, we have this component and this component right here. Okay, this one right here is going to be E sine of 60. This is also going to be E sine of 60, and they're going to add together to give us 2E sine of 60, which we end up with as the square root of 3E. Taking the 2 components, multiplying them to squaring them and then adding them, and then taking the square root of the sum, we end up with the square root of 3E. So the total electric field, which would be directed straight up, it's going to be the square root of 3 times KQ over R squared. The total electric field is in the plus Y direction. Okay, so now let's go ahead and look at this again. The vector representation of the total electric field as a sum of the electric fields due to charges A and B. Okay, so if I take this piece right here, actually they have it grouped together. And this arrow, by the way, is going up, not connected to this one. Okay, so if I take this piece right here and I form my parallelogram, do y'all remember the parallelogram? Here's my one vector, here's my other vector. Now what I'm going to do is take this one right here and I'm going to clone it. And what I'm going to do is I'm going to drag it up to here, and notice that I have added them tip to tail. Notice where the resultant is going to be. It's going to be straight up from here to here. Okay, two negative charges, A and B, are placed at the corners of an equilateral triangle. What is the direction of the net force at point C? Go ahead and pause the video if you need to. Okay, so let's take a look and see if you have the correct answer. Hopefully you didn't choose B, but you chose D. Remember, these two charges are negative. Their electric fields are going to go inward towards the charges, not away from the charges. Two negative charges, A and B, are placed at the corners of an equilateral triangle. What is the magnitude of the net electric field at point C? So now again we want the magnitude of the electric field strength. Okay, so let's see if you chose the correct answer. Hopefully you chose B, square root of 3 kq over r squared. Okay, that ends our lecture for this unit on electric forces and electric fields. If you have any questions, please post them on Edmodo.